Okay. So basically, in yesterday class, we were discussing the gravitational force, and we were starting the gravitational force with the help of Newton's third law. Okay. and and then we said that the forces will be equal and opposite from both the masses m1 and m2. Okay. So this is the mass m1. Okay. M1. Okay. And that is m2. Okay. That is m2. Okay. So for any of the mass, uh, if I increase the magnitude of one of the two masses, okay, the gravitational force will going to increase, right? So this is the first thing. If I increase any one of the mass, so gravitational force will be increased. Okay, so m1, m2, right? So gravitational force is basically directly proportional to the product of masses. Okay, and if I increase the separation, okay, if I increase this separation, so the gravitational force is going to decrease. Okay, so the second thing is the second relation is inversely proportional to r square. Okay, and if I combine them, the r square is due to like it is there because of the separation and the values, right? So if I combine them all, so it will give me f is directly proportional to m m m1 m2 or m capital M and small m divided by r squared. Okay, r squared, right? And then we can say that to remove the proportionality, we can just say f is equals to gmm over r square. Okay. Okay. Where g is a gravitational constant. Okay. So is so this is universal gravitational constant.
How did you get this? F is directly proportional to m1 into
Mm.
m2 over r square.
I just combine these two things. Okay. So
Okay,
that's how.
okay,
Okay.
okay.
So okay. And this has a value, g has a value of 6.67, 6.67 exponent negative 11. Okay. And meter square per kg. Okay. And this constant shows this is a universal constant. It remains the same forever. Okay. And this shows that gravitational force is very weak in nature. Okay. So this constant basically shows you that gravitational force is very weak in nature. Okay. So this is the first thing, or this is a law. Okay. Now we have to write its wording as well. Okay. So the wordings are okay. Let me just take it. Perfect. So now if I write the Newton's law of gravitation, its wording, so we used to write gravitational force, gravitational force is directly proportional to the product of two point masses. Okay, and inversely proportional to the square of their separation. See, so separation. This is the Newton's law of gravitation. Okay, and in this law, you have to mention two things that are very important. Um, Newton's law of, come on, Newton. Rho. So Newton law of gravitation. Gravitation. Okay. So this is the Newton's law of gravitation. They'll ask you like in 2 to 3 mark for the definition. Okay. And you have to mention this thing. This is the important thing. The product of 2 point masses. Okay. And you have to mention the square of their separation. Okay. Okay, these are the two things that are very important in this concept, okay, in this definition. Now, for this law to be useful, we do some of the assumptions, okay, and those assumptions are the first thing is that we consider the masses perfectly spheres, okay, masses are perfect spheres, okay. The second is masses uh, are point in nature, point in nature, which mean point mass is basically the mass is basically when the mass is basically viewed from a very far distance or a very from a very long distance. So it looks like a point mass, right? Like if you're traveling in the plane, okay, and you try to see from out from the window, so you see everything like a point, okay. You can see the details in it, okay. So this is how the point in nature. This is what the point nature means, okay. And the third thing is masses are isolated in the space. Okay. The fourth thing is all the mass is concentrated toward the center. Okay. And yeah. So these are the assumptions. We can make one more assumption. Uh, Uniform density of the mass. Okay, so these are some of the assumptions that we have to make in order to apply the Newton's law of gravitation, right? So these are the assumptions. Okay, so okay, done. Now, so the overall formula is this one. Okay, this is the formula, by the way, and this is the gravitational force formula. Okay, now if you want to use this formula to make it into the gravitational field formula, so the gravitational field will be um, gravitational field will be um, will look like this. G is equals to uh, force upon mass. Okay, this is the gravitational field. Okay, force per unit mass, right? And if we put the formula, if we put the value of F, so it will become G equals to GMM over R squared divided by mass, right? So you can cancel these mass out and you'll be left with G is equals to GM over R squared, right? So this will be the formula for the gravity that we'll be going to use. Okay, we are not allowed to use a gravity as 9.81 in always the cases, right? Or in everywhere. We have to use some other things as well. Okay. Now, so if we try to find out the values of the gravity, mm, okay. So if we try to find out the values for the gravitational field, so let's say that you have the Earth right here. You have the Earth. Okay, let me have my Earth. Earth. There's my exam. I'm actually taking all the various pictures from the. Come on.
Small g is gravitational field, right?
Sorry, small. Yes, gravitational field. Okay.
Yeah, okay.
Do I have it? Come on, I don't. Okay, fine. Um, Geographic North Pole and South Pole. I don't want that. Not this one. But fine, just ignore it. Okay, so let's say I have this planet. Okay, and let's say if I am at a distance of, if I am, let's say, this is, let's say, Earth. Okay, Earth. Okay, so Earth has a mass of 6.0 into 10 to the power 24 kgs. Okay, and the radius of 6.4 exponent 6 meters. Okay, this is the values for the Earth. Okay, now if I try to find out the gravity at the surface. Okay, so gravity at the surface, so how will it be? So you just need to use gm over r squared. Okay, and for g you just put 6.67 exponent negative 11. So yeah, and then you put 6.0 exponent 24, and then you put 6.4 6.4 exponent in 6, and you can square it. Okay. Yes, can you calculate the value, please?
Yeah, okay. 1 second.
How much?
I'm getting the answer, but I'm not getting it in standard form. 1 second.
No, why 6 point?
6.3.
You didn't square it? It should be
Oh,
9.81 something, no? Because you're finding the gravity at the surface of the Earth. So I am, by the way, getting 9.77 newtons per
one
kg.
second.
Okay. If I find the gravity 100 meter above, okay. So gravity at 100 meter from the surface, okay. So it will be just the same thing, okay. Like 100 meter means over here, okay. This is, let's say, 100 meter, okay. So it will be, everything remains the same, but you just need to add something in your answer, and that will be your thing, okay. Just okay. So you just need to add 100 over here, okay, and you have to square it, okay. So you still get the same thing as 9.77 newtons per kg, okay, newtons per kg, right? And this is for the second case. The third case will be, if we try to find out the gravity at 100 kilometers, or let's just do at 100 meters, okay. So 100, we did 100 meter, 1000 meter, let's say 1000 meters, okay. So again, the formula remains the same and everything remains the same, and but over here you just need to do 1000 and you have to square it, okay. So when you add the 1000, I don't think so it will be changed, 9.767, okay. So it is just getting 9.767, okay. If you go at gravity at 100 kilometers, okay, now it will going to be changed, okay. 100 kilometers mean 1 exponent 5, okay. 100 kilometer mean 100 into 10 to the power 3, right? And you have to square it, right? So when you find that value, okay, So that will going to be exponent 3. So now it is 9.47 newtons per kg. Okay. One more thing. If I have,
Uh,
yes,
it is decreasing, right? Because we are
yes,
moving further away.
yes, but it is decreasing according to the inverse square law, right? Like near to the planet, there it is not that much decreasing, but as you increases the distance, so let's say the last thing, gravity at 1,000 kilometer. Okay, so you just have to do the similar thing. Okay, so it will going to be 1,000 exponent 3. Okay, and so it is just 7.31 newtons per kg. Okay, so this is how the value of the gravity is basically changing, right? Around the earth, okay, or around the surface, right? So this change in the gravity is basically known as the inverse square law. Okay, the pattern of the change in gravity showing the inverse square law. Inverse square law. Okay, and that is G is inversely proportional to R squared, right? Fine, that's it. Okay. So this is how the gravity value changes, right? Now, I'm stopping right here because you have the next class right now. So I'll be starting the class tomorrow, like half an hour earlier, okay? To get the things done. Okay. So I'm keeping this class till there, okay? And we'll start the next class earlier, okay? And we'll try to complete the things, जो भी whatever the things are remaining, okay?
Okay, what time?
At 3 my time, okay?
Okay,
Because okay, like 2 your time, okay?
yeah.
Okay, chal. Okay, take care. Lafis.
Love is. Love
Lafis.
is.